In reality, what happens is that, see, suppose I have data like this. So my trees are here. And you have drawn, you would normally draw your decision boundary like this. Your margin, so not decision boundary, your margins like this. And you would draw your like this, isn't it? But let us say that on a river, there is a boat house. Have you seen boat houses? A house on a boat. So first I said, you don't have houses in the river. Obviously, there are. So let's widen the reality and say, what if you notice a house shining right here, right? And let's say that there has been some flooding and a tree has, and you notice that during flood season, trees get washed out. And so a tree has gotten washed out here. Right. Now, there is a bit of a problem. You could say that, and not just washed out here, let's say that it has gotten washed out. Trees can get washed out pretty far. What now? You could say, my margins are now, let me use a different color. My margins are now, well, I can't flow it like this. My margins are now this and this, right? And this yellow house sitting on top of this margin, isn't it? Would you agree? My river now is very narrow that I can flow through the data. This is the best river I can do. So far, so good. Yes. And of course, then you would flow another river, another, median through that as a decision boundary. So
can't we curve the river?
No curving. All rivers are straight in this ideal world. For now. Right?
Can you break into sections?
Not allowed. So at this moment, stay with the fact that rivers are straight.
And completely clean.
And complete. Right. Yeah, what's it?
Railway track.
Sort of like a railway track, yes. So we have this, or think of it as a canal, right? Some engineers, when they bring canals, they're completely straight. Actually, you can always tell a canal from a river because rivers will bend and canals will go straight. The great, I believe it was Salvador Dali, the great painter, who used to make a very interesting statement. So I learned a little digression. At one time, I aspired to be a painter. I learned from a great painter, my teacher, who had graduated from Oxford. And he was really a master, amazing painter. So one day he told me a remarkable fact, and I think it's attributed to somebody. He said that in nature, you never find straight lines and edges, rarely. But in engineering, human-made things, you rarely find smooth flowing curves. Everything is geometrical shapes, right? So you can tell a canal from a river because the river will sort of meander its way through the land and a canal will go straight. Just something to keep in mind. But anyway, at this moment, we are pretending that it's a straight river for now, straight section of the river. So now if you were to pick which of the river looks better, the blue or the pink, intuitively to you?
Blue still looks better.
Yeah,
blue still looks better, but a blue, according to this theory, is wrong, isn't it? The only permissible river is the pink one. So this brings the idea that, see, data has errors, right? So trees get uprooted and sail into the river. Houses develop lifeboats, houseboats, right? So you have to keep a little budget. So suppose we did this. We say, hey, let's keep a budget budget C for errors, right? And what is the error? See here, suppose I take epsilon 1 is the degree of the error. So you say that the decision boundary for this, or the how far it is from. So by the way, this distance is m. The distance that the median is from the banks is, let's call it m, margin. So you say that for this guy, distance from the distance for the lighthouse is not m. It is actually approximately it is a part of m. Actually, the way you say it is 1 minus epsilon, where epsilon takes values from 0 to 1, m. So if it is a small error, distance would be exactly equal to, so for example, the lighthouse is here. It's practically m. The distance from the decision boundary is m. So the bigger the error, the further away it is, right? The further inland it is, right? Are we understanding this, guys? Right? So you say that we allow an error for this point, this error epsilon. Now that is okay. So we said this point will granddaddy in. We'll say, no, you don't have to be, we don't consider you to be the support vectors. We know that you're a houseboat. And this tree has gotten uprooted. So we'll forgive it too. We'll say that we are going to ignore it, right? Not consider it to be one of the crucial points. So these points that you choose to ignore, they will each have an error associated with them, isn't it? Because this is your, how much inland you have come is given by your epsilon I, right? Now, you don't want to allow too many errors. Otherwise, what will happen is, if I start making a decision boundary that looks like, let me choose a color I haven't chosen, pink. Will that look different? Okay, I'll try to pick a color I haven't chosen. Okay, forgive me. Suppose I make a decision bound, like if I make my river banks like this wide river bank, why is this not okay?
You're gonna crash.
Yeah, there are too many houses and too many trees that you have to sort of ignore, isn't it? You don't want to do that, because being too relaxed means you have overshot the mark, isn't it? You're not going to the bank, and as Kate said, you're going as a boatsman, you're going to, with your boat, you'll crash into the banks. So you don't want that either. You want to avoid crashing into the bank, but you allow for some mistakes because you believe that there are mistakes in the data, right? So you keep a budget. And so this brings us to a concept that you keep a budget such that epsilon 1 plus epsilon 2, whatever number of epsilon k's you have, it is less than equal to some budget C. Are we together? You say you think of each error as amount you have spent, and your total budget is, and think of error spending, error penalty. I think penalty would be a good word to do. The error penalty that you are facing. So E epsilon I is the error penalty. Effectively, you can think of it like that, right? And you say that the sum total, therefore, of epsilon I has to be less than equal to C. Right.
So Asif, who will decide what is the value of C?
Very good question. Remember, I told you that every model has hyperparameters. The cross-validation will tell us what is a good budget. Like by just looking at how many testing errors we get, we'll have to adapt the cross-validation. We'll have to adapt the C. Now it's a hyperparameter. So let's put it this way, guys. We realize that the distance. Now, what is the distance of these error points from the decision boundary? Distance of this point xj of xi is equal to, what is it? It is beta naught plus beta hat dot xi, right? Dot xi, or let me write it in my notation, which I prefer. It is this angle bracket. This is it. And we are saying that for some mistake, it has to be basically greater than, equal to some amount m1 minus epsilon. Means the margin must be the distance from the margin. You should still have reasonable distance from the margin, but you allow for some errors. Now you also realize that beta hat magnitude is equal to 1. That's a constraint, isn't it, in this equation? So for example, if you write this equation, but you multiply it by 10, now your beta hats are no more unit vectors, isn't it? They still go to 0, but they don't. So this is a constraint. And the last constraint is that you have sum of all the epsilon i's is less than equal to some budget. It is, do you see how intuitive it is? What I'm saying is just common sense, right? You're just saying that you're allowing that all the distances should be such that up to a certain error amount, most points should have 0 errors. So if you're beyond the margins, if you're beyond the blue margins, what is your error? So think about it this, guys. If I have a house here, with respect to the blue line, how much mistake am I making?
None.
None, because this is more than the margin, greater than the margin away from the decision boundary. And so this point is fine, no errors. Errors are only there only when you are inside the margins. So then so this is it. And therefore we write this equation, modified equation. This equation is, these are called, so this adaptation of the maximal margin classifier in which you allow for a few errors up to a certain budget, because that's how data looks, right? This is called the soft margin classifier. Some people also call this the support vectors classifier. I don't. I reserve that for the machines. But soft margin classifier, use this word, soft margin classifier. Why soft? Because you allow some things, some data points to be inside the margin. Whereas, Pradeep, this answers your question, right? In the original thing, you were pretty harsh. You said nothing in the river, clear separation of data. But now you're allowing up to some error amount, or up to some budget C, that in between the margins, the two types will be mixed up.
Right, sir. But I had slightly different question, that there could still be data which cannot be separated in categories.
In other words, they cannot be linearly separated.
Right.
So one easy example is, suppose you're inside a circle, is all the cases are positive and outside all are negative. You realize that there is no straight river going through this.
Correct.
So we will come to that, but let's not get there. Huh?
Okay.
Remember, world is simple. So at this moment, now suppose this soft margin classifier allows for a situation in which your data is like this. Mostly houses, and then green trees, right? And some green trees even growing so far in, but mostly green trees here, and maybe some houses, one house spouting here, right? Which is a huge error, because now you're making big mistakes, right? And you still say that, hey, you know what, I will still, because my budget is good, I will still flow my river. I believe my river flows like this.
Right. So, sir, what is the, like, I get some of it, the question, the answer for the question which I am going to ask, but I wanted to get your opinion. What is the point of having the maximum margin between two classes of the data? Because technically, unless the data from one class doesn't cross the decision boundary, we should still be good.
Yeah, I'll tell you why. See, let me answer that question. Why the maximal margin? We did that, but see, what happens is that suppose I have a lighthouse. So let me make these lighthouses again. I mean, this houses again. Huh? Suppose you get only data that is like this, and you get green data. Even in the simplest form, you get green data that is like this. Sorry. These are your trees. Are we together? So you take seven samples of data, so eight samples of the data, like this, or 9, or whatever it is. This is your sample. Remember that any data set is always only a sample, right? And now let's take another sample of data, which looks like this.
Oh, got it, sir. Yeah, you answered it earlier.
Yeah, I did, right? So suppose I have this, right? And this is even here, some, and this green point. So let me finish the argument as a review, right? And let's say that you have tree, somewhere tree, somewhere tree, somewhere tree, somewhere. So now you notice that the data is different. So now let's flow one decision, one kind of a blue margins wide like this. But instead, if you had flown a pink margin like this, 2 points. Yeah, so now obviously the blue has wider margin than the pink one. Now look at this data. Does your pink one survive with another sample of the data?
No.
No, but blue doesn't vary much. It's more or less the same, isn't it?
Correct.
And so what you say, you always want a model that is robust in the presence of sampling. It shouldn't change every time you take another sample of the data.
All right.
And that is why you prefer the maximal margin.
Yeah, so it's a out. That's why it is very robust against outliers.
That against
I mean,
yeah. Of the data. All right, guys. So what I just taught you are two major algorithms. One of them is we learned maximal margin classifier. These are also called the hard classifiers, hard decision, because they make hard margins. You're not allowed to have anything in between. And we learned also about soft margin classifiers. Some people call these as support vectors classifiers, but doesn't matter. We also learned that lighthouses. Now, in the soft margin classifiers, what are the lighthouses? So go back to the intuition. If you want to row your boat carefully, do you only need those lighthouses on the banks of the river, or you need it in the middle of the river too? Right? So suppose, look at this. Let's go back to this problem. When you are rowing your boat, let me take a yellow color. So this is again intuition, guys. So suppose you're rowing your boat. It is okay. These lighthouses have lit up. This also has lit up. And this tree has lit up, Christmas tree, right? But you realize that that is not enough, because you can go and hit this tree that's in the dark floating in the river, or you could go and hit this house. Are we together? So what do we need to do? We need to light up the things inside the margin also. Otherwise, you go hit them. Make sense? Right? So that is the intuition. You need to go light them also. So in other words, they also need to become lighthouses. Or another formal way of saying it is that support vectors, in the case of soft margin classifier, the support vectors, lighthouses, are all points, data points, of course, data points on the margins. Sorry, I take that back. This is atrocious spelling. On the margins and between the margins, between the margins. Another way to put it is inside the river. Are we together?
That's
And
good
we
because
have
I
a
was
budget.
wondering how you wouldn't hit that as a boatman if you forgive these arrows, but you don't mark them. But if you mark them also as support vectors, at least you can avoid hitting
Yes,
them.
exactly. So you need to light up those, otherwise you'll hit them. Right? So this is sort of obviously I've made it quite with analogies, but this I hope gives you a sense of this whole thing that we are leading up to, the whole maximal margin thing. So think of support vectors as lighthouses and the decision boundary as the path that the boatsman will take, right? Always. And the boatsman would prefer that the banks were not too close. You don't capsize. They were far apart. It's a wide river. Then you get most of the intuition with for these things correct. And those are support vectors. So next I will go to, it is 12:13. It's time we took a break.
One quick question, Asif, just to correlate with what we have done before.
Yes.
So does this two boundary, two margin kind of a model converge into a single linear model, single linear boundary model in any kind of conditions?
No, the decision boundary is always single. No? It's the median between the two margins.
Okay. So, okay, you're combining, okay.
Yeah. See, between these two margins, there will be the decision boundary. Remember,
Okay,
decision
this is
boundary
only to get, okay, got it. It's only one boundary still,
yeah,
but there are two margins.
that
okay.
is, you need these two symmetric margins. Right? The median, it is the median between the margin, is the median.
Okay.
Margins. So now things are beginning to look rather interesting. From here, now we will take the next leap in the next session, in which we'll say that, no, wait a minute, rivers never run straight, right? They wander around, or more prosaically, in data, you almost never get linearity. You see a lot of non-linearity. So how do we deal with non-linearity in the data? That is a problem we are going to solve in the after the break. Now, that is going to be a bit of a session. It's 12:15. Let me first review what we have done. So today we used the analogy of a river and its banks and the boatsman to learn about the concept of maximal margin classifiers. Right? We want to flow the widest river we can through this data set, not the narrow, because narrow rivers will change, the shape will change for different samples of the data. Right? Those lighthouses are called support vectors. And the path that the boat must take in order to safest path to avoid capsizing against the bank is literally the median of the river, and that is the decision boundary. So river banks are the margins, the formal terminology. So let's say this entire thing in more formal river, flowing the widest river through the data is the same as having a maximal margin hyperplanes, right? Creating two maximal margin hyperplanes. All points on the maximal margins are called support vectors. The median of the median plane between those between the margins, maximal margins, is the decision boundary, right? And this is it. Then you soften it up a little bit for reality, and you say, well, we'll allow for a budget of mistakes. When we allow for a budget of mistakes, we then can still flow a fairly wide river, but we get a classifier which must agree to this constraint that, see, in the hard margin, where are we? Why did everything disappear? Okay. In the hard margin, Strange. My screen went blank. What is happening? Let's go slowly. Yeah. In this hard margin classifier, what is the constraint that each of the points should do? The green ones, let's say, let me just write it. The green points, let me call this as +1. Y is +1, right? Because you need a label, and the label for reasons will take as -1. Now observe something. Suppose we consider this distance as positive distance and this distance as negative distance from the decision boundary. So what do you want for all trees? You want distance of a tree is greater than equal to the margin. Would you agree? This is what you want.
Yes.
Right? And for all houses, you want, what do you want here? For distance of all the houses should be, this is what, -m, should be less than equal to -m. So it could be even more negative, right? Would you agree that this would be the reasonable constraint for the houses? Right? Now, it turns out that you can play a mathematical game. What you do, it's just a cute game. The meaning is exactly this. Remember, we took this points as y is equal to -1. So see what happens. What is y on this side? Yi, let me just say di, yi times d, well, d, the house I, the house point I. What will it be? If I multiply this equation by -1, it will become +m, which begins to look like the tree equation where y we set as +1, isn't it? So on this side also, we could say the same thing. This yj times distance of this tree j is greater than equal to m, isn't it? Do you see that, guys? Simple, no? Which is exactly the same equation as this. So the way you write the constraint is, the more elegant way that you write the constraint is that for maximal margin hyperplane, the constraint is yi times the distance of a point xi is greater than equal to m, right? In other words, this is your main constraint. In the case of this is the hard margin. In the case of a soft margin, you allow some latitude. You say, you say d xi is, if not greater than m, it is greater than m minus a small, at least a small part of m, right? Greater than equal to something like this, right? You relax it a little bit. It can be in the river, or you can have a few mistakes. Right. This is it, guys. Huh? So that's actually going back to this. I said that this is equal to, but actually I should say yi, because for houses, the constraint is different. So it is this greater than yi di, which is y items this is the distance, is greater than that thing. And remember, beta is a unit vector, which you say, emphasize by saying it must be of size 1, and you have a budget. You cannot go on making accepting mistakes and saying ignore this, fine, this is fine. This is your main budget. So so what happens when your budget is 0? If your budget is 0 in this situation, let's look at this. Which would be the margins? The pink, the purple, or the blue? If your margin for error is 0,
Purple.
Blue.
budget for error is 0. If C is 0,
Oh, it'd be the ugly pink one.
yeah, that's right. So you would say C is 0 would be this situation. There are no mistakes here. No errors allowed. On the other hand, what about the purple one? Purple one, you would say that C is big. Lots of errors allowed, isn't it? Because you see between the purple lines, lots of houses and trees, they seem to be floating in the water. And what about the blue line? Hopefully the blue is, C is, for this, C is hopefully optimal. But how would you know that it is optimal? How would we know that it is optimal?
The errors are within budget.
No, when you take the data and you make predictions on test data or on validation data, you will find that C gives you less validation errors, isn't it? Less errors on validation. So you have to, so what now it says that how would I know what is the optimal C? You search, typically you take lots of budgets, right? C from 0 to, C will go from 0 to whatever big value, let us say 100, and then you take little intervals, 0, 0.1, right? Even 0.001, very small, then 1, 10, etc., etc. You take all sorts of values of C, and you have to keep on making your classifier for each value of C and see which gives you the least validation errors, right? That is the correct, or that's the optimal choice for C. So C is the budget in this. Remember, so now let's think in terms of bias variance trade-off. If the budget is very small and you take another sample of data, will the model change?
Budget is small. Yes.
Immediately change, right? Yes. So when there is no budget, you have high variance in your models. Well, that's what it maps to. But on the other hand, if C is too generous, look at the purple line. It is suffering from high bias data. You take another sample, more or less it will draw the same thing, but it is overtly simple. It's not, it's going to misclassify a lot of points and throw them into the river.
Sort of like regularization.
Yes, and that's what it is. A bias, yes. So it's like that. So the bias situation is too big a C. Variance situation is too small a C. Somewhere in between is the optimality between the bias variance, is the bias variance trade-off, the right value of C. So far, so good, guys. And that is it. If you have understood it so far, then you have pretty much gone through the large part of the intellectual journey. From here onwards, there is an interesting twist that takes us to the nonlinear domain and into the true, what are called support vector machine algorithm. So let us do that after a 10-minute break.